Now for the next question, we want to understand the behavior of a spring. Now, instead of a spring, I use the expedient of just making a couple of chains of rubber bands that have force properties somewhat similar to that of the spring in the problem. Okay, if I stretch these rubber bands out, right now it takes no force. The further I stretch them, the more force it takes. The longer the rubber band chain, the greater the force. I can see what happens if I suspend a 200-gram mass, which is about a 2 Newton weight, from this chain. Okay, here we go. And it stretches the chain out this far, probably about 6 or 7 centimeters. Now, I can put this 500 gram mass on here, and it's going to stretch the thing out quite a bit more. Okay, there we go. Okay, and that looks like, well, probably 30 centimeters or more. Incidentally, I strung 3 rubber bands in a chain because with one rubber band, the force that I exerted to stretch the 3 rubber band chain out would have only stretched this one out about this far. Okay, whereas the 3 rubber band chain would stretch with a similar force much further. And to be even more convincing, in a minute I'll hang one of the masses here. Okay, so here we have the chain. Same force I exerted before stretches the chain a lot further. And of course, it's easier to stretch just one chain than it is to combine them into one and stretch the 2 chains. If I put the 200-gram mass on here, it stretches, but only about 1/3 as far as the 3 rubber band chain stretched. And similarly, we'll stretch a single rubber band. Actually, that stretches pretty far, doesn't it? Not sure I made my point on that part, but you get the idea. Okay, so what we're saying is we have a rubber band that for every centimeter of stretch requires an additional 4/10 of a Newton of force. So we're going to stretch this to a position 20 centimeters from the equilibrium position. Now, equilibrium is just where the spring or the chain or whatever is when it's unstretched. Okay, and 20 centimeters from equilibrium means we add 20 centimeters to the length. Okay, so if we stretch this rubber band chain, or in this case a spring, with this characteristic, we call this the force constant, generally denoted K. If we do a 20 centimeter stretch on a spring that exerts 4 newtons of force per centimeter of stretch, of additional stretch, then we get a force of 4/10 of a Newton per centimeter times 20 centimeters, or 8 newtons. Now, between the original length and the additional 20 centimeter length, the force goes from 0 here to 8/10 of a Newton here. Now, that's not really true of the rubber band chain. If I did 3 rubber bands in a chain, that would be about right. 3 chains of 3 of these rubber bands. But you get the idea again. The force on this spring will go from 0 newtons to 8 newtons, so that the average force, if the force goes up linearly, and this tells us that it does go up linearly, if it stretches the same amount for every centimeter, then the force changes linearly with the length of the stretch. Then we can just add these two and divide by 2 and get the average force. So, now as far as the force by the spring, what's the direction of the force? Okay, so if I'm stretching this rubber band chain to represent the spring, and if I stretch it out from here, and I'm going to stretch this end, okay, what's the direction of the force that's being exerted on my fingers? Well, that direction is, let's see if I can get it this way, right? Okay, and what way am I pulling? To go from here to here, the direction of my force is this way, right? So, the average force acts opposite to the displacement, so the work I do, or the work done by the spring, okay, and this is the work done by the spring, and I should probably find a way to specify that. It's clear from the statement of the problem that's the work we're trying to find. Just to be complete here, delta W is negative because delta W means the work by the spring. I could put subscripts on it and stuff, but I don't want to do that right now. So that the delta W, understanding again, this is the work done by the spring, is average force times delta S, negative 4 newtons times 20 centimeters, negative 80 newton centimeters. Now, of course, you could express that as Newton meters or joules, and we actually do in this case because we want to just relate this to the standard unit. A centimeter is 0.01 meters, so negative 80 Newton centimeters is negative 80 newtons times 0.01 meters, and that gives you negative 0.8 Newton meters or negative 0.8 joules. Okay, so the elastic potential energy then, well, let's back up. Okay, this is the work by the spring. Okay, specified here, added a specification here. The spring does work negative 0.8 joules. Now, what's the change in elastic potential energy of the spring? Well, it's equal to the negative of the work done by the force, equal and opposite to the work done by a conservative force. Now, let's talk about conservative force for a minute. We've talked about it before. Just as gravity is a conservative force, if I raise an object and then drop it, the same force works coming down as it did going up. For a rubber band, that isn't actually true. You can actually put the rubber band over your top lip and pull it this way and then let it go this way, this way, this way, this way, this way, and you can feel that sometimes it cools off, sometimes it heats up. That's an indication that not all the work that the rubber band that you're doing against the rubber band is still going to be there. The fact that in some cases you heat up the rubber band means there's energy lost as that heat dissipates into the atmosphere. I'm not going to talk too much about that, but my point is that the rubber band force is not completely conservative. Unlike gravity, if I go up here and then come back down, the force exerted by the rubber band as I return is not exactly equal to the force exerted as I go up. However, for an ideal rubber band or an ideal spring, we assume that it is so. It's not, you're losing probably 10 to 30% of your energy with a rubber band. With a good spring, it's going to be much less, maybe just 1%. So that an ideal spring, without going into any more detail than that, and it wasn't very much detail, an ideal spring is one whose force is conservative, whose force is the same at every point coming back as it is when you're going out. Now, I've got change in elastic potential energy is equal and opposite to the work done by the conservative force. I've got rubber band force here, and I'm going to change that because, of course, the original problem asks about a spring and not a rubber band. Okay, again, the change in elastic potential energy in the case of the ideal spring is equal and opposite to the work done by the conservative force. And you can read this: a force exerted by an ideal spring is conservative. And remember that this is consistent with our definition of change in potential energy, the definition being equal and opposite to the work done by a conservative force. So, again, change in elastic potential energy is equal and opposite to the work done by the conservative force exerted by the ideal spring, and that work is negative 0.8 joules, so that the change in elastic potential energy is equal to negative 0.8 joules, or 0.8 joules. Simply saying, if this is the spring, I stretch it 20 centimeters, and it's got now 0.8 joules of potential energy. And if I release it, well, there it goes. Okay, 0.8 joules of potential energy to the far wall of the lab. I lost a little bit scraping on my thumb there. I'll whine a little bit, but I'll recover. Okay. Summing up very briefly, our ideal spring exerts a force of 0.4 newtons for every additional centimeter. The force increases by 4 newtons for every additional centimeter of stretch. So if we stretch 20 centimeters from the equilibrium, the no force point, we get maximum a force of 8 newtons. If we stretch it from the 0 to the 8 centimeter point during the stretching process, we're going to start with 0 force, end up with 8 Newton force. The force is linear because of this. So we can average the two. We get a 4 Newton average force. We multiply that 4 Newton average force by the 20 centimeters, and we get 80 Newton centimeters, or negative 80 Newton meters, or 80 joules. The force that is exerted when I stretch, the force exerted by the spring. If I stretch it this way, the force is that way. But the displacement is this way, so that the work is negative. So we get negative work done by the conservative force exerted by the spring. By definition of potential energy change, that's equal and opposite to the change in what we call the elastic potential energy of the spring. Thus, the elastic potential energy of the spring is 0.8 joules, and if we release the spring, we get that 0.8 joules back.